Hello friends, welcome back to Rising Mathematics. In this video, we are going to solve this example based on the concept of delta derivative of the function in time scale. So example is, for a given time scale t, which is union of the set containing number 0 with set of all points of the form 1 divided by 2n plus 1, where n is some number from the set n naught, and a function f defined on time scale t such that f of t is sigma t. Then we have to find the delta derivative of the function f at point t in set t to the power k. So firstly note that for a given time scale t, one is left scattered maximum point. So for the formation of set t to the power k, they have replaced this one from the given time scale t. Now we will start our solution. Consider a non-zero point t in set t to the power k. So t will be equal to 1 divided by 2n plus 1. Hence n will be equal to 1 minus t divided by 2t. Now clearly f is continuous at this non-zero point t in set t to the power k. And further we have sigma t is infimum of set of all points s in time scale t such that s is strictly greater than 1 divided by 2n plus 1. So this set will contain points of the form 1 divided by 2n minus 1 plus 1, 1 divided by 2n minus 2 plus 1, 1 divided by 2n minus 3 plus 1, and so on. So infinitely many points will be there. And clearly infimum of this infinite set will be the number 1 divided by 2n minus 1 plus 1. So we get sigma t equals to 1 divided by 2n minus 1 plus 1. Substituting value of n, we get sigma t equals to 1 divided by 1 minus t divided by 2t minus 1. So rearranging this, we get sigma t equals to t divided by 1 minus 2t, which is clearly strictly greater than t. So every non-zero point in set t to the power k of the form 1 divided by 2n plus 1 will be a right scattered point. Now to find derivative at this right scattered point of the given function, we will use this theorem. So statement of the theorem is, assume f is a function from time scale t to r and let t is point in set t to the power k. Then we have the following. If f is continuous at point t and point t is right scattered, then function f will be differentiable at t with delta derivative of the function f equals to f of sigma t minus f of t divided by mu t. Now in our case also we have f is continuous at point t and t is right scattered. So delta derivative of the function f at point t will be f of sigma t minus f of t divided by mu t. Now we know that f of sigma t will be sigma of sigma t by definition of f, and f of t will be sigma t. Again mu t is sigma t minus t, since mu is the forward gradientless function. Now from here we have sigma t is t divided by 1 minus 2t. So sigma of sigma t will be sigma t divided by 1 minus 2 times sigma t minus sigma t divided by sigma t minus t as it is. Again after solving this, we get f delta t equals to 2 times sigma t square divided by 1 minus 2 sigma t multiplied by sigma t minus t. Substituting value of sigma, here we get f delta t equals to 2 times t divided by 1 minus 2t square divided by 1 minus 2t divided by 1 minus 2t multiplied by t divided by 1 minus 2t minus t. Further simplification gives f delta t equals to 2t square divided by 2t square multiplied by 1 minus 4t. So we get delta derivative of the function f at point t equals to 1 minus 4t. So this is the delta derivative of the given function f at a non-zero point t in set t to the power k. Now what will happen if we consider t equals to 0? So next, for t equals to 0, we have sigma of 0 is infimum of set of all points s in set t time scale t such that s is strictly greater than 0. Now clearly here infimum of this set is 0. So we have the point t equals to 0 is a right dense point, and we can clearly observe this thing for the given time scale. So here sigma is right dense point. Now in order to find the delta derivative of the function f at this right dense point t equals to 0, we will use this theorem, which states that if a function f from time scale t to r and if f is this function and t is a point in say t to the power k, then we have the following. If t is right dense, then f is differentiable at this right dense point t if and only if the limit s tends to t f of t minus f of s divided by t minus s exists as a finite number, and the derivative of the function f at this right dense point t will be this limit. Now we are going to use this theorem to find the delta derivative of the function f at right dense point t equals to 0. So we have f delta of 0 is limit s tends to 0 sigma s minus sigma 0 divided by s minus 0. So we have just applied theorem here. So this is equals to limit s tends to 0, sigma s will be s divided by 1 minus 2s, sigma of 0 is 0 and this s minus 0 will be s. So this limit is 1. So we have the delta derivative of the function f at 0 is number 1. Therefore, the delta derivative of the function f at point t will be 1 divided by 1 minus 4t for all points t in say t to the power k. Since for t equals to 0, if we substitute t equals to 0 here, we will get 1. So the derivative of the function f at all points t in say t to the power k will be 1 divided by 1 minus 4t, and this completes our solution.